All right, guys, welcome back again to our CCIE preparation. I know we're getting kind of close to wrapping up OSPF. We've actually moved into the next section of OSPF, which is authentication. I'm actually going to be covering both of these topics today, OSPF authentication as well as authentication enhancements. And then I believe that tomorrow, well, actually, it would probably have to be day after tomorrow, Thursday, we will go ahead and do our summarization section, and we'll wrap up OSPF, and then we'll get into DMVPN. We still have a lot to cover. We're only about halfway through our lessons here, but we're getting further along, which is a good thing. So today we're going to focus on OSPF authentication. We're going to be using this topology, which is saved in the Google Drive. So if you want to load this topology, you can. It's the same topology that we've been basically using for most of the previous OSPF lessons that we've talked about. So in this section, we're just going to talk about OSPF authentication. It's not really an overly complicated discussion. We're going to talk about what are the different supported types of OSPF authentication that exist. We're going to take a look at configuring and troubleshooting. What are some of the debugs that we can run? You know, some of the messages that we can identify that will allow us to identify whether there's a mismatch in authentication type or a mismatch in authentication keys. It can be a little bit confusing. The debugs are actually relatively simple, but you may have to end up troubleshooting this information when you go into the CCIE lab in the T-shoot section. So we want to be able to identify what we're looking for, even in some show commands like show IP OSPF interface or some debug commands. All right. The goal of authentication, of course, is to protect the control plane function of the router. We're trying to prevent what we call an injection attack, where somebody joins the OSPF routing domain, or EIGRP for that matter, any kind of routing domain, and they try to inject routes into the routing domain by simply identifying what that we're actually running OSPF, and then having the ability to identify that OSPF domain and join that domain, which by default would be available. Because we use multicast hello packets to perform neighbor discovery, anybody that's running OSPF would be able to process and utilize those multicast hello packets to be able to discover information about the network. Even if it's a client, for example, running some software to capture information, typically multicast is going to be flooded through a layer 2 network. All right, we just don't want some random device usurping our routing domain and either injecting false routes or creating black holes in our network by injecting or advertising null zero routes or something like that. We can even force routes to be withdrawn from the graph, if you will, or we can force constant SPF calculations, which can then result in some sort of denial of service attack on a routing domain. Okay? Authentication in this particular case, when we're dealing with IPv4, does not mean encryption. All right? In the CIA triad, we're always trying to protect three different things: confidentiality, integrity, and availability. In this particular case, by implementing OSPF authentication, particularly with OSPF v2, where the payload is sent in clear text, we're trying to protect specifically integrity and availability. All right, and I'm going to describe how that process works using a shared secret password that we're going to configure. Now in OSPF v3, we do have the option of adding the third of those three corners, which is encryption, using a one-hop IPsec tunnel between the peers. We're going to be doing a whole bunch of IPv6 stuff later on. We haven't really talked a lot about IPv6 in the past few lessons, so we're going to get into discussing IPv6 quite a bit a little bit later on. All right. Now, when it comes to OSPF, there are actually, in essence, three different authentication types. Authentication type of 0, we'll see this in the actual payload, in the actual packet header information, the OSPF packet header information. An authentication type of 0 simply means that we're not doing any authentication presently. All right, so if I actually come into my device here, let's go into this link from router 4, and I do a capture, I can see the hello packets, and within those hello packets, we can see an indication that authentication is actually represented in the hello packet. So let's take a look. Here's my OSPF hello packet. This is my header. So it's not actually the hello packet. And this is actually a very important point when it comes to authentication in OSPF, is it's actually contained within the OSPF packet header. The hello packet header is here, and the hello packet data is here. So the authentication piece is not actually included physically in the hello packet. It's included in the OSPF packet header. We can see an authentication type of null, which is 0. That's the type code that we're using to represent the authentication type. And we can see authentication data is just basically filled in with zeros, indicating that we're not doing any kind of authentication. The reason why this is particularly important is because it is part of the OSPF header and not part of the hello packet. That means that it doesn't matter what type of packet it is. Let's see a reply, not that reply. Let me generate some data here. I'll go into my router here, and I'm just going to bounce an interface just to generate some updates. Okay, so show IP interface brief, config T, interface Ethernet 1.0. We'll do a shut and a no shut on that interface. And we should see in our capture here that we're getting hello packets. We should get an update and so on. So here's our link state update. And sure enough, authentication is part of that because it's part of the OSPF packet header. I keep clicking on that reply thinking it's a link state acknowledgement. That's what I'm looking for. Even the link state acknowledgement includes the authentication type. So this moral of the story in this particular case is that every single OSPF datagram, if authentication is applied, is going to have to be authenticated in the OSPF process. All right? So we have 0, which is no authentication. The next option that we have with OSPF is what we call simple password authentication, which is type code 1. We're going to configure that and take a look at that as part of our configuration steps and verification and troubleshooting in this lesson. We try to avoid using that because passwords are sent in the clear. And then we have type 2. Type 2 means that we're using some sort of cryptographic process, using a challenge response hashing process to do the authentication, which can either be MD5 or SHA. And there are some enhancements in that as well. It's still type 2, but we can also run some of the latest encryption algorithms like SHA-256 or SHA-512. We can enable OSPF authentication under the global process, or we can enable it under the link level. Let me pull up the rest of my routers here, because we're going to eventually do some different configurations. We'll play around with different options between the different routers here. And talk about, because it is slightly different than what you would see with EIGRP with regard to configuring authentication. Some of the traditional methods for configuring authentication with OSPF only allowed us to essentially establish a shared secret key, but we couldn't necessarily use a keychain. And that's one of the enhancements that we're going to talk about a little bit later on, is the fact that we now have the ability to use a keychain with the enhancements in the newer version of OSPF. All right, so we'll talk about that. Sorry, I was just getting my tabs kind of in order here. We'll talk about that, and we're going to apply some of these configurations. We can enable OSPF under the global process, meaning that I can go into the routing process, router OSPF 1, for example, and say area, router 1 is in area number, well, we'll go area 0 for now. Area 0, and you'll notice that I have an authentication option here. And I can specify whether I'm going to do message digest or potentially whether I'm going to do SHA. This particular iOS, unfortunately, is limited to message digest. I might have to pull up one of my iOS V routers to show you some of the enhanced configurations as part of this exercise as well. All right, so I could say if I go into the global process, authentication, and I hit return, that means I'm doing simple authentication from this particular router. Now, what's interesting is that I've enabled the authentication process globally for Area 0, so that means any interface that's participating in Area 0, but the parser didn't really give me an indication that this was going to break my OSPF adjacencies. Because I've actually enabled authentication, simple plain text authentication on router 1. Eventually what I should see is that those neighbors, at least in Area 0, should go away. Let's take a look at our, there we go, waiting for the dead timer to expire. So it is indicating we have lost our adjacencies with router 4 and router 5 in Area 0 because I've enabled plain text authentication. But I haven't actually given the router any way to authenticate. So if I was to go to, say, router 5, for example, and do the same thing, router OSPF 1, and I do a Area 0 authentication, by not specifying that I'm using message digest, I'm simply deferring to the simple password authentication process. Notice that I did get my adjacency back. Now, there's a common misconception as to how this authentication occurs when I haven't even specified an authentication credential or an authentication password. Since we're already doing a Wireshark capture on router 4, let's go ahead and do, well, it's a broadcast domain, so we should be able to see the hello packets coming from the other routers. All right, so I'm looking specifically for hello packets from router 5. Do show IP protocols. Now we'll do interface brief. I think this one is .3, yeah. So this guy's .3. So if I look at the hello packets coming from .3, right here, actually any packet would have worked. You'll notice here that authentication type has been set to type code of 1, simple password authentication, but there is no authentication data. It's all zeros. Meaning that we've enabled the authentication process. So we all agree that we're going to use simple authentication, but in this particular case, authentication is actually not occurring. Somebody could capture this data. They could say, oh, you're running simple password authentication, but the authentication data field is blank, which means there is no password. All right. So that's an example of implementing OSPF authentication under the global process as opposed to on the link level. Now, what if I did choose to implement MD5 authentication? Let's go ahead and enable MD5 authentication on the link between router 1 and router 2, which is going to be Ethernet 1.1 or Area 1. I'm going to do it globally under router 1's configuration, Area 1 authentication message digest. And I'm going to do it on the link level on router number 2. So there's really no golden rule that says use this method over this method. The function is still the same. The global process obviously is going to allow us to apply an authentication method to all the interfaces that participate in that particular area. But doing it at the link level is as effective, it just doesn't cover as many interfaces. So I'm going to go into Ethernet 1.0 on router 2, and I'm going to enable authentication message digest under that interface. Interface Ethernet 1.0 IP OSPF authentication. Again, I have an option of specifying null, which is basically type 0 authentication. Or I can hit a carriage return, which would indicate that I'm doing simple password authentication, or I could simply say message digest, and that is my option. You might say, well, wait a minute, why would I ever put null on the interface? since essentially that's what's running by default anyway. Well, let's say, for example, you wanted to enable MD5 authentication for the entire area, but you wanted to disable the authentication process on that particular interface. What we apply to the interface is going to override whatever is done under the global process. So I could enable plain text authentication under the global process for the area, but then I could also enable MD5 authentication or message digest authentication under the interface for that particular interface. That's going to override what's happening with authentication on the global process. So if I come in here and I do a capture now on router 1's interface, let's come over here, let's do a capture here. All right. What I should see is message digest authentication is enabled. But again, we're not sending any data. We're not actually sending any authentication data. So this is a hello packet from router 2. Here's our header. Authentication type type is cryptographic, so type 2. But that's interesting. We see a couple of different variables here. We see an authentication data length. We see a key ID, and that's actually very important. We'll talk about that in a second. But there is actually authentication data. What's interesting about this is that we're providing a hashing process. So a hashing process is taking place. We're not just sending null data in the cryptographic data field. This is a hash of the packet payload information. So this router is sending a hello packet, and it's generating a hash of the data that's actually contained in the hello packet itself. So this is the result of the hello packet. So this could potentially provide a level of integrity and certainly authentication, but here's why it's not. Because we don't have a key specified. A key ID of 0 means that we're not using keying material in the hashing process. Somebody could easily capture this packet, modify the hello parameters, modify the payload information within the packet, recalculate the hash and send it on, and the hash would be verifiable at the other end because we don't have any secret material that's included in the hashing process. Let me kind of draw what I'm kind of trying to put down here. All right, so let's say that I did have a process where I've got a router on the left here and R1, and I want to send data to R2 using a message digest authentication option. Now, normally I would have some sort of keying material that would be shared in common between the two routers, key 1 or key 10, whatever it is, and we'll see how to configure that a little bit later on. And I've got my hello packet that I'm trying to send over to the router. I want to make sure that that hello packet maintains its integrity, and also want to make sure that router 2 knows that it can trust that information and then trust that it comes from a reliable source and not some rogue device in my network. So by taking that keying material, which is secret to both of the routers, and taking the hello data and running it through the hashing process, we come up with our message authentication code, or our hash, if you will, and we send that hash along with the hello packet. Okay? So when this router on the other side receives the hello packet, it's going to go ahead and process that data through the MD5 process, along with the keying material that's configured on that router, and it's going to come up with a hash, and it's going to compare this hash to this hash. Are they equal? Then nobody's modified the information. Okay? As long as the keying material is kept secret, nobody's going to modify that information or be able to modify that information because they don't have the secret sauce that's necessary to generate a valid hash that's going to be verified by the router on the other side of the link. Very similar to how keychains work with EIGRP. Very similar, okay? The problem is because we're using key ID 0, which essentially means no key, there is no keying material that goes into the hashing process, which means the only thing that's being hashed is our hello packet. Well, who's to say somebody in the middle can't intercept that hello information, modify it, regenerate a new hash, and send it on its way? Because there's no secret material, there's no secret key, we don't have any integrity, we don't have any authentication. So again, just because we've implemented, it appears as though we've implemented some sort of hashing process. Because the key ID is 0, that means it's not really truly going to provide us any level of protection, if you will. Okay? This could very easily be an output that you would see on the written exam or on the lab exam to identify, hey, what type of authentication are we running? Is this communication secure? And it appears as though it's secure, but it's actually not, because there's no keying material that's utilized. All right? So we're going to, of course, set up different options and take a look at what this looks like. We're going to first set up a password on the links between router 4, router 1, and router 5 so that we can see what the simple password data looks like in the packet header and why that's not considered secure. And then we'll go on and set up our MD5 authentication. Just to review, though, really quickly, link level configurations always override whatever's done at the process level, always. It's also really important to understand that regardless of how you configure the authentication key or the authentication method, the key is always going to be done at the link level. There is no option to apply a key in the global process, all right? So if I do decide to apply a key and my key is being applied to SHA versus MD5, and I haven't specifically enabled SHA on the link level, but I've enabled MD5 on the global level, it's obviously not going to work. The keying material or the key that we specify, and we'll see the syntax in a minute, the key that we specify has to match whatever we're identifying either at the link level with regard to the type of authentication we're going to run or at the global level. All right? All right? The key IDs have to match to do any kind of authentication. As you can see, we do share the key ID information. When we send the information, we don't send the key, of course, that would be silly, but we do send the key ID. So if I'm using key ID 1 and that secret key is my secret key, you have to have my secret key established for your key ID 1 as well. We can use, in the newer version and the enhancements of OSPF, we can do keychains where we can have multiple keys and we can rotate keys like we did with EIGRP. But we'll take a look at that towards the end of the lesson today. All right? All right, the keychain authentication is supported. We'll take a look at whether or not this iOS is going to support it. I think it should be supported in 15.x, but if not, we'll go over to our iOS V router and we'll take a look at the keychain authentication in iOS V. We'll just set up a couple of routers just back to back and do that configuration. All right. Now, another thing to consider is how does authentication work on a virtual link? Because if you think about the context of a virtual link, you've got a router that might be attached to area 0, right? So that's my router attached to area 0. And then you've got another area here. We'll just call this area 1. And you've got some other router over here, and maybe there's even routers in between, right, that are allowing us to communicate from area 0 through area 1. And then finally, I've got my discontiguous area, area 2, and I've got some routers in this area that need to communicate over that virtual link. So we're trying to establish this virtual link from this router to this router. So you have to think about that for a second. Does that mean that if I'm doing authentication between, well, just give them some numbers here, R1 and R6, does the authentication need to only be configured between R1 and R6 over the virtual link, or am I going to have to apply the same authentication across all the routers in that domain? All right. Virtual links are always tied to area 0. So whatever authentication that you're applying to area 0 is going to apply to the virtual link itself. Okay? The inheritance rules that we have for the virtual link interface, you know, as far as it being attached to area 0, they're going to apply to what we see with authentication as well. All right? The virtual link is actually the interface. I'm going to show you the syntax a little bit later on. We'll go ahead and create a virtual link, and I'll show you how the authentication works there. But the virtual link is actually the physical interface itself. The key actually goes on that interface. But we do have the option of specifying the authentication type on the interface or on the globally in the OSPF process. The link level of the virtual link, in this particular case, because you're thinking, well, what interface would I tie to the authentication process? Would it be this interface or that interface, right? The answer is none. All right, because the link level of the virtual link is actually global under the process, at least how we define it. We don't go into a physical interface. It's a little confusing the way I'm describing it, but I'll show you a simple way to configure that, and then also how do we verify its functionality. Keep in mind that virtual links run as demand circuits. So even if you're applying additional configurations, if, for example, I'm adding authentication onto the virtual link after the fact, and my authentication configuration is not correct, I may not be aware of that until the virtual link tries to establish itself again. So make sure you always clear the virtual link after you set up the authentication to make sure that the authentication process is set up completely correctly. Because you won't actually realize any issues until you try to establish the adjacency over that virtual link. You try to send hello packets over the virtual link. Okay? We've already done some of the basic adjacencies and looked at some of the basic command line. So now what we're going to do is really kind of take a look at more progressions. We're going to add a simple password in area 0. We're going to do our MD5 password in area 1 and take a look at the Wireshark captures. We already looked at the Wireshark capture for the authentication type of 0, which is null, and already mentioned the fact that because it is listed in the OSPF header, that means that the authentication has to apply to all OSPF packets. All right. Now, technically, I guess if you want to be argumentative, you could say that authentication is actually enabled even though we're doing an authentication type of none, because we are representing that authentication is turned on. If I go to back to my diagram here and I start doing a Wireshark capture on this serial link, I will see that the authentication type is null or none, but it's still defined as a type. It's still type 0. We've already seen that. I'll just pop it up again here and show you real quickly. Okay. All right. So again, in our hello packet, we do see in the packet header, authentication type is null. Authentication data is specified, but not being used. So technically, this is considered an authentication method. It just means that we're not really doing any authentication. All right, so we've already done authentication between the peers in area 0 with simple password authentication. Like I said, if you go into the process, let's go back to router 4, and I do router OSPF 1, area 0 authentication. If I hit a carriage return, that's going to default to simple password authentication. And we've already done that. We can see that we saw in the Wireshark capture that we have a type 1 authentication, but there's no data because we're not sending a password. All right. To me, I think the parser should really tell you if you set up an authentication method without a password, because obviously your goal is to have some sort of authentication. but you know, it's not really occurring, right? Technically, it is a valid config. It's just we're authenticating without a password, which again is basically like no authentication. All right. Now, if I come in here and I do a debug, let's take that off actually. No area 0 authentication. And I do a debug IP OSPF adjacency. Let's do a hello also. We should get an indication that we have a mismatch authentication type. Input packet specified they're using type 1. We're using type 0. So we're not going to be able to go through the process of establishing our adjacency. Eventually, the adjacency will go down. Notice that it hasn't gone down because our dead timer hasn't expired. Show IP OSPF neighbor. It has gone down. I must have missed the message. All right. So we are getting mismatched authentication type. So it does recognize type 0 as an authentication type. All right. We don't have a misconfigured password. It would actually tell us if we had a misconfigured password. It's just a mismatched authentication type. So let's go ahead and turn on authentication. We should see that we go through the adjacency process. So I'm going to go into config T, router OSPF 1, and I'm going to do area 0 authentication again. I should see adjacency come up, and we'll just go through our standard adjacency exchange. All right, going from the down state to the init state to the two-way to xstart exchange, loading in full. Okay. Notice in this process, though, we didn't really see any reference to authentication. This isn't the appropriate debug to see that. We're just debugging the adjacency process. So it doesn't indicate that we are running authentication. There should be one area, though. Let me do an undebug all real quick. There should be one area that would indicate, we probably have to do a different debug. We certainly would see it with a Wireshark capture, but yeah, we're not seeing it with the debug adjacency. We might have to do a different debug, but we don't see really that there's any indication that authentication is taking place. All right, authentication is turned on. We don't have a password. It's 2 separate steps to do the configuration. So let's go ahead and apply that configuration now. Show IP interface brief. Interface Ethernet 1.0. And I'm going to do IP OSPF authentication. Notice I have the option to specify the type again, which we don't need to do. We've already done that in the global process. But again, whatever I apply here is going to override whatever whatever's configured in the global process, if you will. All right. So the question is, how do we apply the password in this particular case? If I implement IP OSPF, I can look at the question mark and I can see it's actually 2 distinctly different commands. IP OSPF authentication enables the authentication process, and authentication key allows us to set the key. All right. Now also notice with authentication key, I can specify the key. This has nothing to do with the message digest key if I was applying a message digest key, because you can notice here that we don't really identify whether a key ID is specified or not. So this is my plain text password that would be applied to my simple authentication process. CCIE or die is going to be our key. All right. Oh, it's truncated. Okay. That's okay. The fact that they even limit it to 8 characters is kind of lame as well. Let's try die. Yeah, there we go. All right. So do show run. Interface Ethernet 1.0. So we can see that our key is applied, CCIE or die, and that is case sensitive, of course. And we don't see that authentication is applied here, but it's applied to the global process for area 0. So that's another thing that they may try to do to you is they will mix and match the configurations. In some cases, they'll apply authentication on the interface. Some cases, they'll apply authentication in the global process. But authentication is definitely applied. If I do a show IP OSPF interface Ethernet 1.0, right at the end of that output, we can see simple password authentication has been enabled. So if I go back to my Wireshark capture, trying to figure out which one it is. I think, yeah, router 4 Ethernet. And I look at the hello packet from router 4. Let me get the IP address of the interface here. 14.2. And I look at the capture from that router. I should now see the password in the authentication header information, the OSPF header information. Plain text, clearly we're not going to use this method to authenticate our peers because somebody could just simply intercept this information and join the domain anyway. Okay. Now let's do a debug back on router number 5. Debug IP OSPF adjacency. And we'll see, again, an error message once I receive a hello packet indicating now that there is a mismatched authentication password. All right, mismatched authentication key, clear text authentication. So now we know that we're at least running the same authentication method, but there's an issue with the authentication key. All right, unfortunately, there's no way to apply the key under the OSPF process. We have to apply the key under the interface. Show IP interface brief, config T, interface Ethernet 1.0, IP OSPF authentication key, CCIE O die. So we should get our adjacency back for that particular interface because we're running simple password authentication, and there's our adjacency. Okay. Well, that's in. Oh, yeah. I'm still getting an error from router 1. Makes sense, right? Because router 1 is still claiming that it's doing simple password authentication as well. Show IP interface brief. Interface Ethernet 1.0. IP OSPF authentication key. CCIE ODIE. Now we should get our adjacency there as well. Okay. So it's not really a complicated configuration. I mean, this is the kind of stuff that we would talk about in CCNA, really, with OSPF authentication. But, you know, we don't want to miss it just because you might get stuck with a question on the exam about it, on the written exam or the lab exam where you have to fix authentication. All right. Let's go ahead and fix the authentication between router 1 and router 2. That, if you recall, is the authentication that we're running between these two routers, R1 and R2, which is MD5 authentication. You can probably already guess how that's going to go. So if I go to router 1, show IP interface brief, I believe that is subnet 12. So that's going to be Ethernet 1.0, interface Ethernet 1.1, IP OSPF authentication. Well, we can't use the key option because that only applies to our plain text authentication. So what we need to do is we need to set the message digest key. We specify the key ID. I'm going to go ahead and use 1, and we specify the method, which could be SHA or could be MD5. In this particular iOS, we don't have SHA available. And then I specify the password. Okay. All right. Now these passwords could be encrypted using the service password encryption option. So if I don't specify how the password was entered, then it doesn't really matter in this particular case. because it's going to default to plain text. It's going to assume that I'm putting in a plain text password. But I could put in a 7 followed by a level 7 encrypted password if I wanted to. In this case, we can, well, let's just go ahead and make them, I like this one. We'll go with that. All right. Now, again, I would get an authentication, a password mismatch. If I go to router 2, and I do a debug IP OSPF adjacency, debug, there we go. I should see mismatch authentication key, but it's going to give me a little bit more information, right? It's going to say no message digest key 1 on the interface. So now it's telling me I don't even have a key ID 1 specified. So there's no way for me to verify the authentication process. But if I go into the router, which is Ethernet 1.0, and I say OSPF message digest key 1, CCIE ODIE, all right, oops, MD5. Now it's going to give me a different error. It's going to say, okay, I have a key ID 1, but now there's a mismatch in the actual key string, all right, because I set the other side to CCIE or die, and I set this side to just CCIE or die. So it's a slightly different message, but it indicates that I am using MD5 key number 1, but now it's saying mismatched authentication key. Whereas in this particular case, saying mismatched authentication key, but it was saying, look, I don't even have a key ID 1. All right, so if I fix that, we'll get our adjacency. Oops, got to take out the old key first and put in the new key. All right. And now we go through our adjacency. Now, what does this look like from the show output? If I do a show IP OSPF interface Ethernet 1.0, we can see the message digest authentication is enabled, and we're using key ID 1 to send the data. All right. Same thing would have to match on the other side of the link as well. Now, this is a salted hash. Not that the salt is necessarily going to protect against man-in-the-middle attacks. It's going to negate the usefulness of, say, for example, a rainbow table if we're trying to calculate a hash based on pre-calculated hashes. So a salt is included. You know, we kind of already gone through the process of how the hashing process helps protect against man-in-the-middle attacks and also ensures integrity. There's even kind of a degree of authentication, right? Because even though the password is a shared secret password, only the devices that are participating in our domain should know what that password is. So we are getting somewhat of an authentication, even though it's not individually authenticating a particular peer. We could, for example, set up different keys for different peers, and that would be another way of potentially authenticating a peer. If I go back to my debugs here, my Wireshark captures, I should see in the packets here, that's our other one. Let's go back to this one, I believe. Yeah. So we're seeing now that we're using authentication cryptographic key ID number 1, and the hashing process is being calculated. I'm not sure if the sequence number is used as the salt or if there's another value that's part of the hash that's used as the salt. I didn't really kind of go in and into the RFC and really take a look at those details. But there is a salt value which protects against rainbow table attacks, okay? Brute force attacks, if you will, okay? So we've gone through the process of verifying simple password authentication. We've gone through the process of verifying MD5 password authentication, specifying a key ID, We can see that the authentication type here is cryptographic. It doesn't necessarily specify that we're using MD5. You can kind of infer that we're using MD5 because of the hash itself and the length of the hash, because we have a 128-bit output hash. So you could essentially identify what method of hashing we're using based on that. And hopefully with the IOSV routers, we'll be able to do the enhanced configurations. Otherwise, we'll just have to look at some reference documentation and show you how that's done. Okay. So we're doing message digest authentication between the peers using a password. Obviously, you want to use a secure password that's not really that easy to get. Okay. All right. Now, if I was to look at an LSA, pretty straightforward. The LSA information is not going to be encrypted. We still have the cryptography applied, but when I look at the actual payload information, I can see all of the information in plain text. The only way to prevent this from happening would be to overlay some sort of IPsec VPN or some other encryption method on top of the link between the two peers. Okay. You might potentially be able to do that at layer 2 if you're using MACsec, but that's only going to be on your peer-to-peer links between the two switches, not on the route between the router and the switch. In OSPF v3, which we'll take a look at later on, we are able to form a one-hop IPsec tunnel using the built-in IPsec AH mechanisms that are part of the IPv6 specification, but we can't do that natively within OSPF v2. Okay. Now, if I wanted to verify whether or not the hash was salted or not, using this hashing tool here, I can go ahead and take my password to hash, CCIE ODIE. Actually, we were using OR in this case. We should see that the output hash is not going to be anything like the actual encrypted data here, right? And that's for two reasons. Number one, when we're doing the hashing process, it includes payload information of the packet itself, which allows us to continue to verify the integrity of the payload, but it also includes a hash. It doesn't really matter, though, how many times I hash the password. It's going to end up resulting in the same hash output every single time. I'm switched back and forth between those two just to show you that the hashing process, the result of the hash was different. So this is a way for us to verify that the password is not the only thing that's being challenged. We're actually, or hashed. We're actually hashing the packet information as well. I have no way of really capturing that information and putting into my hashing tool here, but it is included. All right. The output hash takes variable length or MD5 takes variable length data on the inside, on the input, and it generates a fixed length output hash every single time, which is an MD5 hash. All right. Now let's go ahead and set up a virtual link here. This will take a little bit of time. Let me go ahead and stop all my captures. All right, and actually kind of kill all these windows here. Quit without saving. Quit without saving, and quit without saving. All right, kill this as well. So we're going to create a virtual link, and I want to create the virtual link through Area 1. So I've got to create a network that is discontiguous. So I'm just going to go into Router 2. All right, and I'm going to try this without having to create an additional router. Do show IP interface brief. Interface loopback 100. IP address 100.100.100.100, 255.255.255.255 or 0. IP OSPF network point to point. Router let's just do this. IP OSPF 1 area 51. Okay, so now this prefix, the 100, 100, 100.0 prefix, is not going to be recognized by router 4. Do show IP route OSPF 100.100.100.0. Sorry, there we go. Network's not in the table because it's not going to be sent into OSPF because it's a discontiguous network. We got to create a virtual link across area 1 in order for that to work. So I need to get the router ID of router 2, show IP protocols, and I need to get the router ID of router 1, do show IP protocols. All right, and I need to go into router OSPF 1 and say area 1 virtual link to 5.5, or sorry, 2.2.2.2. And I have to go into router 2, area 1, oops, router OSPF 1, area 1, virtual link 1.1.1.1. And that should allow me to reach that destination. Let's see, make sure I did the right routers. I think I did. Show IP interface brief. Show IP OSPF virtual link. Let's see, demand circuit, it is up. Might take a little while for the convergence to do show IP route OSPF. I should see that route come in over that virtual link. Area 1 virtual link.
Scott, you made a comment earlier in another class that it always has to be in area 0 for a virtual link.
The router that I'm establishing the virtual link to needs to be in area 0, right? So router 1 is where the virtual link is terminating. We're creating this virtual link between these two routers. The virtual link does not have to pass through area 0. It just has to be attached to area 0. So we've got this loopback here, which is loopback 100. That's 100.100.100.100, and that is in area 51. It's running OSPF. If I do a show IP OSPF interface, I should see that loopback 100 is running in area 51. Let's go take a look at that real quick. Show IP OSPF interface. Loopback 100 is up, area 51, it's attached. So I'm curious why we're not seeing it on router 4.
Did you make it from area 51 to area 1?
No.
Area 0?
No, you specify area 1 as the transit area. Show IP OSPF virtual link. Not router 4. Sorry, do show IP route OSPF. Okay. So I'm curious why we're not seeing it. So when you're establishing the virtual link, you need to establish it through the area. The transit area is the area that you specify. You don't specify area 0 as the transit area. The virtual link is being created through area 1. Yeah, so I forgot that we have authentication applied between these two routers, but we haven't applied authentication to the virtual link. So it's not going to work, right? We need to apply authentication to the virtual link as well because the virtual link is part of the area. So let's go ahead and remove the authentication for now. And I don't need to remove the key, I just need to remove the authentication. Oh, I did it under the interface. Do show run interface Ethernet 1.0. Interface Ethernet 1.0, no. IP OSPF authentication message digest. And on router 1, do show run interface Ethernet 1.1. I did it under the area. Router OSPF 1, no authentication, no area 1 authentication message digest. All right. And this is the thing that you have to consider when you're dealing with the authentication of the virtual link. All right, and so I'm just taking off the authentication between the two routers, show IP OSPF neighbor. I still have an adjacency with router 2. Actually shouldn't go down because we're not resetting the link. The authentication changed before the dead timer expired. But we should be seeing 100.100.100 now. Still not seeing. So we got a few configurations that are lingering from a previous exercise. You can't create virtual links over special area types. Not possible. It's kind of interesting that it actually showed us that the virtual link was up and functioning, but a virtual link is not allowed to run over a special area type. So we have to disable that as well. Router OSPF 1, no. Oh, that's area 2. Okay, so that should be okay. We're not creating the virtual link over area 2, area 1. Okay, so this goes back to what I was telling you at the beginning of this lesson. The virtual link inherits the properties of area 0 because it is a link that is actually participating in area 0. And because we have simple password authentication enabled on area 0, it's expecting that the virtual link should be running simple password authentication as well. So what we need to do is we need to apply simple password authentication to the virtual link, but we can't do that under the global process because, again, the virtual link is not really part of area 1. It's using area 1 to establish the link, but it's really part of area 0. So the question is then, how do I apply, if I've already got the virtual link with simple password authentication applied on router 1, because router 1 is the router that's tied to area 0, if I go to router 2 and I do the same output, show IP OSPF virtual link, you will see that simple password authentication is not established. It looks as though the virtual link is up and functioning, but it's not going to pass data because we have an authentication mismatch essentially. So what we have to do is we have to go into our OSPF process and we have to say area 1 virtual link, and you'll see that one of the options going to router 1, one of the options that we have is to specify authentication and authentication key or message digest key. We can't enable message digest authentication on the virtual link directly, but we can set the key on the virtual link. So we need to specify both the authentication method and the authentication key in this particular case to ensure that we can, maintain that continuity over to area 0. All right. This would be a very tricky thing to figure out if you're faced with this on the troubleshooting portion of the test, where why isn't the route going in? Why isn't it going in? Well, we know that there's a virtual link created. The virtual link shows that it's up and active, but it's not passing information. So let's go ahead and set the authentication type. All right, and we're going to set the authentication key to CCIE ODIE. And hopefully, now that we've gone through all the different iterations, identifying whether or not we're running a special area type, kind of removing the authentication between the peers within the area, which we can go back and reapply, by the way. We need to see if we have authentication enabled. It is. Show IP OSPF virtual link. Simple password authentication is enabled here as well. So let's see. Still no route. Okay, well, let's continue on and troubleshoot. So we found the issue. The issue was on router number 1, even though it inherited the authentication method. Simple password authentication was applied because the virtual link on the ABR for router 1 ties the virtual link to area 0. We did not have a password applied. Let me scroll back up because I kind of did this while I wasn't recording. We had the virtual link established, but we did not have the password applied to the virtual link. So because authentication passwords or key IDs and key strings need to be applied at the interface level, I was inheriting the fact that I was running simple password authentication, but I didn't have a way of authenticating the peer because I didn't apply the password to the virtual link on this side. I did it on this side because it was required in this particular instance because this router 2, is not participating in area 0, so it's not even inheriting an authentication type, if you will. So we had to specify authentication, which tells us that we're going to do simple authentication. And then we had to specify the authentication key, CCIE ODIE, which had I left that part out, the virtual link would have come up because we were already running simple password authentication based on the inheritance of area 0's configuration on the virtual link. So now if I go to router 4, finally I should see 100, 100, 100, 100, which I do. It's coming in as a type 3, which makes sense because it's coming in from area 51, but it does have the do not age, which indicates that it's coming over a virtual link. If I do a ping to 100.100.100.100, everything should work out just fine. Okay. You guys follow me on that? Because I kind of went through a couple of different steps to troubleshoot the issue. I took off authentication between router 1 and router 2, which, by the way, we could reapply. It's completely independent of the authentication of the virtual link. So right now we're running authentication between router 2 and router 1 for the virtual link, but we're not running authentication between router 2 and router 1 for the physical link. We're simply authenticating the virtual link to area 0. So we could actually apply another set of authentication properties to Ethernet 1.1 and 1.2, or 1.0 on router 2. So if I come into interface, well, let's do router OSPF 1, area 1 authentication message digest, interface Ethernet 1.1, IP OSPF authentication message digest, key 1 MD5, CCIE or DIE. Oh, the key's already there. All right, so that should be fine. I need to go and apply it to router 2 as well. Show IP interface brief, config T, router OSPF 1, area 1 authentication, area 1 authentication message digest, interface Ethernet 1.0, IP OSPF message digest key. I just want to make sure it's still there. Excuse me. So the key's applied. Do show IP OSPF interface, Ethernet 1.0. We can see that we're running message digest authentication between router 1 and router 2. If I do a show virtual link, show IP OSPF virtual link, we can see that we're doing simple password authentication on the virtual link. So they're independently configured is my point. They're not the same, okay? If I do a show IP OSPF neighbors, I should see that I have an adjacency with router 1. Yep, actually got two different adjacencies. I've got a virtual link adjacency tied to area 0, which is the way that all virtual links get tied, and I've got a physical neighbor relationship with router 1 and area 1. So now we're running not only simple password authentication to authenticate the virtual link to area 0, that would have to match, by the way, whatever I've got configured on area 0 would have to match. The key strings don't have to match because we established the key string on the virtual link, or the key if we're running MD5. But the authentication type would have to match whatever area 0 is. Does that make sense, guys? You could see where this could kind of throw you off a little bit. It even threw me off a little bit as we were kind of going through the process.
Yeah, I get it.
Okay. All right. You need to know the verification steps. As we went through the troubleshooting, I kind of paused the video a couple of times not to take up too much time on the video going through some of the basic troubleshooting steps. Don't worry, you didn't miss anything because I repeated myself after we found the problem. But these are the kinds of things that you might have to troubleshoot. You need to understand, okay, I walked through it. I even backed off some configs to say, okay, let's make sure that this is not causing a problem. And then by reviewing the configuration and with the help of my peers, we were able to identify the misconfiguration. Okay? So let's talk one more thing before we wrap up tonight's lesson, the enhancements to OSPF authentication. Mainly, it's just new cryptographic algorithms and a slight change in the syntax and the format of the syntax. We use a keychain format similar to what we would use in EIGRP. If I go out to Google here, all right, and I do a quick search on IP OSPF Authentication Keychain example, I should see in the configuration example the new cryptographic standards that are supported. Notice here OSPF RFC 2328 allowed message digest authentication, but now RFC 5709 allows for HMAC SHA cryptographic authentication, which includes SHA 256, SHA 512, and so on. All right, so let's do keychain and see if we can see an example output here. All right, we'll see if we can kind of run through the process as well, but I just wanted to kind of talk to you about how we define the keychain. So it's very similar to what we did with EIGRP. We configure it in global configuration mode using a keychain name, in this case simple one. That keychain name is locally significant to the router. It doesn't have to match on both routers. And then we can specify the key IDs and the key strings, the cryptographic algorithm that's going to be used to generate the hash if we're using this key, and we can also specify a send lifetime and an accept lifetime for the key itself. So very similar to what we saw with EIGRP. Now I can go in and create this keychain, but unless I can apply the keychain to the cryptographic process in OSPF, it's not really going to help me. All right, so this is the command that we need to be able to apply IP OSPF authentication keychain and then specify the keychain, but that's obviously not going to be an option. If I do IP OSPF authentication, I don't have an option to specify a keychain. So I'm going to pause real quick. I'm going to see if IOSV will allow us to do this. Give me 1 sec. So what I did is I just added a couple of IOSV routers here. We'll just put a simple network between them using network 10.10.10.0/24. And I've already gone through and configured OSPF on these devices, waiting for the adjacency to form. Show IP OSPF adjacency, neighbor. Geez. All right, there we go. We're in a full state now. So here's the question. If I go into interface, by the way, we're using interface gig 00, show interface, show run interface, gig 00, basic config, just an IP address. If I do a show run section OSPF, you can see that we're basically just running, really simple OSPF. So if I come into router OSPF1, router, this is the test, area 0 authentication, still only message digest in this particular case, unfortunately. So it doesn't look like IOSV is going to allow us to do the enhanced security. So we're just going to have to take a look at this as a configuration example in the documentation here. I'm not even sure that you would necessarily have to do this in the CCIE lab as well, but we definitely want to take a look at the enhanced cryptographic authentication. So if I'm specifying a keychain, I know I can do that because keychains are kind of a generic configuration. So I can create a keychain globally, keychain, and give it a name, my chain, all right? And I have the option of specifying a key with a key ID. So we'll say key 1. And I have an option of specifying the send lifetime, the accept lifetime, the key string. So CCIE or DIE. And I can say, what is the cryptographic algorithm going to be? So it does give me the option of applying all of these concepts, right? Unfortunately, though, it's not going to allow me the ability to apply it to the interface. We'll give it a shot, but I don't think it's going to because we can't specify it. You know, we may not have to in the case of keychain authentication because we may be able to reference the keychain directly from the interface. But so I can say a send lifetime. This would be when the key is allowed to be used to generate datagrams. The accept lifetime would be when the key is allowed to be used to accept datagrams from a peer. And you can specify multiple keys and multiple key strings. We're not going to do that presently, but that allows us to rotate through different keys. Obviously, you want to make sure that that you have the timestamps are correct on the routers. Otherwise, you're not going to be able to utilize the keys as expected. So we would want to make sure our clocks are synchronized. So rather than type all this in again, I'm going to do a show run pipe section key chain and grab that configuration and paste it over onto router 2. I know I could have done this also in the iOS that I was running on these routers as well. Question is whether or not I can apply this RFC 5709 specification to the OSPF process, right? By the way, RFC 5709 does not define any new types of authentication methods. Type 0 is still null, type 1 is still simple, type 2 is still cryptographic authentication. It defines new algorithms for type 2, but it doesn't change how type 2 functions. All right. The only difference is we have keyed MD5 available. We have HMAC SHA-1 available, which we wouldn't have previously. We have SHA-256, SHA-384, and SHA-512 is available as well. All right. So we can establish multiple keys. We can do time-based key rotation. We can have a single keychain that's used for multiple interfaces, and so on. All right, so we define the keychain globally, all right, and walk through the steps of, you know, what are the different keychain options. Now let's go to the link level and see if we can apply the keychain at the link level. We couldn't do it globally, but now I'm thinking that the global process wasn't necessary. So let's go into interface gig 00. We know it wasn't available on the other routers that I had running authentication. But I would type IP OSPF Authentication, and I should have an option. Okay, so it does work in this iOS. Excellent. Notice here in router 1. Yes, sir.
On the other routers, have you tried creating the keychain first and then seeing if the option was available?
It won't be, but I could give that a shot. Let me do a show run section keychain. Yeah, it's not going to change it's not going to give me that option, but I'll go ahead. I know I'll be able to create the keychain. All right. See, yeah,
like AAA, certain things only show up after you.
Yeah, sure, exactly. Yeah, notice we got an error here indicating that we couldn't even specify the cryptographic algorithm. It does allow me to create a keychain, but that's for EIGRP authentication. which is always, keychains have always been supported with EIGRP authentication. So just to confirm, even though this is a later version of iOS, this version of iOS does not support the RFC 5709 standard. So, but good news, iOS V does, so we can apply it. So if I do IP OSPF authentication, keychain, and then specify my keychain, right? Do the same thing on the other side. No valid authentication key is available on interface gig 00. Oh, we need to...
You got the wrong keychain in there.
Yep, I put in the key string. I didn't put in the keychain. Keychain is my chain. So let's go ahead and take that off. Copied the wrong information. And let's do my chain. I was wondering why I was saying there's no key. I configured a key, but we used the wrong name. Okay. Now I would apply the same thing to the other side. Oops, interface gig 00. And apply the keychain there. Now if I do a show keychain, I should see whether or not the key is valid, the key strings. Because it's, if I didn't specify send or accept lifetime, it's always going to be valid. It's immediately valid and it's infinite. We can see that's an option here. Now, what if I had multiple keys established and I didn't specify the send or receive lifetime for each of the keys? It's just going to use the first key in the list. All right, so even if I had key 2, key 3, key 4 assigned in the keychain, it's going to be use the first available key in the list. All right. So now if I come back and I do my Wireshark capture, it's not really going to look any different between the routers because the only thing that's going to be referenced, the hash will look different, but the only thing that's going to be referenced is the authentication type, which is going to be a type 2. And the hash is going to be a lot larger because we're using 512, SHA-512. All right. So if I look at my hello packet, the hash is significantly larger. Cryptographic process is still type 2. Key ID is 1. But you can see the hash is 512 bits as opposed to 160 bits for SHA-1 or 128 bits for MD5. Okay? So because we jumped around a little bit on this, I just want to kind of refresh this enhancement. This is the only enhancement that we talk about, and it's defined in RFC 5709. You know, you can go and reference 5709 if you'd like. But if I come back to the configuration, show run pipe section router, there's not going to be anything under there. Keychain or OSPF authentication. These are the configurations that were applied. We created the keychain globally, right? Specifying the key string, the key ID, and the cryptographic algorithm that we're going to use. We specified that we applied the keychain to the interface, and we didn't do anything special under the routing process. So the nice thing about this as well that's different from the original configuration is I had to do 2 steps to apply authentication with OSPF. I had to specify the authentication method, and then I had to specify the authentication credentials. Here, I didn't even have to specify the authentication method. I mean, I kind of did because I specified it on the interface, but it's a 1-step process on the interface now instead of applying 2 different commands saying, let's go ahead and run SHA authentication, and by the way, we're going to use this keychain. Because the keychain references the authentication method, right? I could have specified MD5 here. I could have specified SHA-1, SHA-256, SHA-512. And so within the keychain, we're actually specifying the cryptographic process. Does that make sense? All right, guys, that's pretty much it for today's lesson. I'm going to go ahead and stop the video. We'll see you guys in the next